Today it's now time for Jethro's second lecture, Affine and Vertex algebras. Thanks, Jethro.
Okay. Thanks again for the introduction. So in the previous lecture, I said that vertex algebras could be seen as a kind of extension of the theory of affine algebras. So I should explain, or rather, it's time to explain how affine algebras give an important large class of vertex algebras. Okay, so we start with finite dimensional Lie algebra and an invariant bilinear form on it. And from this, you can construct so-called corresponding affine Lie algebra. So it's basically the loop algebra in G, and it's a central extension thereof. So if there's one central element K, and the bracket of other guys looks like this. I'm going to write it in this form: A times a function and B times another function given by AB, product of the functions, plus the central term is given by a residue, but also the bilinear form appears here. G and T, derivative of T, G of T times K. Okay. And to this, you can associate a class of vertex algebras. So first, the universal guy. So it's given by starting with a single vector that's going to be the vacuum in the vertex algebra, in which we're going to say that K acts by some constant, which is called the level. And we're going to say that regular loops annihilate this vector. So this is a module for GT plus CK. And then we tensor over that universal enveloping algebra with the whole universal enveloping algebra. And so there's now a G hat module. So I picture. Okay, so say I took SL2. Then I like to visualize it in this form, right? So somehow at the top, you've got the vacuum, and then you go down by applying these operators. X minus 1 for X in the Lie algebra. You can repeat, keep going down. You could also apply with the index minus 2 and so forth. So here, implicitly, I've sort of introduced a bigrading here, which you can kind of guess what it is from the picture. Now, this is a vertex algebra. So for each A in the finite Lie algebra, there's going to be a field, quantum field.
Could we go back just a step?
Sure.
I thought you wrote down on that board that the affine Lie algebra acting on the vacuum vector is 0, but then your picture seems to say we start with 0.
The positive part. So all the positive powers of T basically want to move up.
Okay.
Well, G power 0 wants to move horizontally, and that's also killed. So like, if you're taking a Verma module, you would want to have, say, F0 acting non-trivially on the highest weight, but we also kill that. Yeah.
So I guess to that question, is there a way when you define the C0 and you define the action, you didn't write down what G minus the negative powers of T?
Right. So this, I mean, I'm not sure how familiar this notation is to everyone, but it's they're kind of, it's defined in a universal way in some sense. So, well, actually, yeah, the answer is that they act by left multiplication here.
Okay.
Right. So all of those elements in the Lie algebra can be embedded into U of G, right? Because G embeds into U of G. So you'd think of them as elements here, and the action is left multiplication, right?
I see.
And your tensor says that some elements, if they're A times T to some positive power, then when you move them to the right, they're able to move across the tensor product symbol to the other side.
I see. What are you tensing? Can you say again what you're tensing? It's a bit small over here. The thing you're tensoring over.
I'm sorry?
The thing you're tensoring over. What is?
That's also a universal enveloping algebra of a Lie algebra.
Cool. What is in the? I can't read it very well from over here. What's in the parentheses?
Oh, I'm sorry. It's U of.
Thank you.
Yeah, all of that stuff. And all of this stuff acts on this one-dimensional module. So, yeah. All right.
Thank you.
Yeah, and then the fact that it kind of looks like this is basically the PVW theorem in the algebras. Okay, so it's a module for the Lie algebra. It's also a vertex algebra. For this, I need to introduce quantum fields, and these are going to be, I'm sorry, so for each element in the Lie algebra, I have all these operators at to the n, right? So I put them into a generating function, multiplied by z minus n minus 1. And now this defining relation, well, you could easily write that in terms of at to the power m and bt to the power n, implies that these, so firstly, they are quantum fields, because if you let n become increasingly positive, you'll eventually, no matter where you start, go off the top of this diagram and start to annihilate. And if you re-express this relation in terms of these quantum fields and then reinterpret that in terms of this lambda bracket that I introduced last time, you get that the lambda bracket of fields A and B, so here A and B are in G, is given by, write this a bit larger. So I guess I should be writing larger, right? People at the back. But yeah, so it turns out that these fields are mutually local, and they have a lambda bracket expansion given by exactly this. So the lambda bracket of two fields is the field associated to the bracket of elements in the Lie algebra, plus this additional term, which involves this bilinear form, okay? What else? So T, again, will be defined. Yeah, so the vertex algebra is generated by all of these operators. So that's one of the axioms of vertex algebra. T will be completely determined by the axioms. So, and it's well defined, so that's okay. And that's basically it. This is the vertex algebra. Vector space, T, vacuum vector, a set of generating fields, and then you can transition to the other version of the definition in terms of associating a field to every element, Borchard's identity, and so on. So we can imitate construction that I did in quite a bit of detail in the last lecture of a Virasoro element. So remember last time I had a half normally ordered product, this guy H with H. So in this case, what we want to do is take some elements of a basis in the Lie algebra and then take corresponding dual basis of G, EI. Dual basis with respect to, well, okay, so now I'm going to assume that this bilinear form that I started with is non-degenerate so that I can take the dual basis with respect to it. And in fact, I want to do a little bit more. I'm going to assume that G is simple and take for this form the killing form. Okay, so we can do this, sum them. And if you start trying to compute the OPE, this guy with itself, you find that it's more or less a Virasoro vector, as we saw last time, except that we have to normalize by something. And this time you don't have to normalize by a half, you have to normalize by a half K plus this number here, H check, which is known as the Joule-Coxeter number of the simple Lie algebra G. Okay. And this you can also check in much the same way as I did in the last lecture. It's quite a fun exercise. Oh yeah, by the way, there are exercises. I guess they appeared on the website already. I'm not sure. Okay. So feel free to do some exercises if you want to. Yeah, what do I want to say? Is a Virasoro vector, i.e., if we take the lambda bracket of L with itself, we get kind of relation 12C times the identity, if you wish. We're now C. So in the last case, we had C equal 1. So I said that the central charge of the vertex algebra yesterday was 1. In this case, the central charge C is level times dimension of G over Again, this weird factor k plus h check appears. And indeed, the fact that this guy appears in the denominator means that you can't really do this if k is equal to minus h check. So you might have heard the term critical level phenomena in representation theory, and really this is a part of that when you consider modules at the level, at the so-called critical level. Oh yeah.
Usually, in the convention we take to construct that is to normalize the killing form by 2 times the Coxeter number.
Yeah.
Since you have not done that, does it change the central charge or something like that?
No, because it does, but not here. Yeah, I guess I should do that. So it doesn't change anything here because these are dual bases. So
The level k is going to define because the choice of k is depending on the.
yeah, that's what I was going to say. So yeah, this is okay, but yeah, I should say that. So yeah, thanks for that. It is important to normalize this form appropriately in order for these explicit formulas to be correct. Yeah, okay. All right, so we're going to avoid the critical level, but the critical level is also very interesting. What else I want to say? So kind of this notion of trying to construct Virasoro vectors in vertex algebras is pretty important, mostly for the geometric side of the theory. So such vertex algebras have a name, or have several names. So I'm going to call them conformal vertex algebras. It's conformal. It is equipped with a Virasoro vector that's above. And this, the property of being conformal is that it has this Virasoro vector, which is just a vector satisfying this kind of OPE for some central charge, with some compatibility with the vertex algebra structure, which is just going to be that T has to be given by L minus 1. So remember that L of Z is written like this, Ln Z minus N minus 2, okay? And depending on the author, there are some additional conditions. You might specify something about the grading of the vertex algebra relative to, in terms of eigenvalues of L0, demand whether they be finite dimensional or not, things like this. But this is this is the core of the definition, conformal vertex algebra. And yeah, I will assume that. Okay, then it's a lemma that if you have a conformal vertex algebra and A is some eigenvector of delta, actually this number delta is often referred to as conformal weight. Okay, so if I have a vector of conformal weight delta, then A sub n, these are operators on V itself, right? And these change the conformal weight by this quantity here, okay? So you can calculate this. And at some point, it really uses this fact here and uses the Borchard's identity, and then you can do this calculation. So it makes sense to define a n. So I'm going to introduce this convention of writing A sub n without these parentheses to be just some shift the grade. So plus delta minus 1, because then AN sends VK to VK alpha, let's say, minus n, okay? And in particular, one of these operators is grade preserving, this now A0. And just a remark that so in this picture of VK of G that I drew, there was a grading implicit, right? So I've done it upside down, but you should think of it as grade 0, 1, 2, 3, 4, etc. That grading that's implicit there is the conformal grading that's induced by this choice of Virasoro vector. Another remark I should say, by the way, is that this L, blah, 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 is called Sugawara construction. And indeed, just as I remarked last time, that you could think of starting with the representation of the oscillator algebra and then doing this construction of L and then arriving at a representation of the Virasoro algebra of potential charge 1, which even irrespective of vertex algebra theory, is quite a valuable thing to do because it's not so easy to get your hands concretely on representations of Virasoro algebra. And the same, I understand the motivation is sort of similar in this case. So representations of affine algebras are somehow a bit easier to understand. And this sort of construction gave a way of producing quite non-trivial representations of the Virasoro algebra. Anyway.
So just out of curiosity, for the free boson, you have this background chart we can play around. Is there something here also? Can you vary this about?
Absolutely, yeah. Now, I can't remember if I put that as an exercise. I think I did. So, remark, in H, with that field H last time, we can shift or, yeah, so we could take that kind of standard Virasoro vector from last time, and then add on any multiple of the derivative of H. And this is again a Virasoro vector. Now, and then B, lambda B, again, there's a computation that you can do with the non-commutative Wick formula. And you get del B plus 2 lambda B plus lambda cubed over 12. And now the central charge changes. It was 1, and now it becomes 1 minus 12 beta squared. So, and this kind of thing, I would call shift or, twist any of these sort of generic words. More specifically, spectral flow is a term that appears in physics that refers to this kind of thing. And similarly here, if you take this guy, L, and you add on any derivative of any element in G, it'll again be a Virasoro vector. And again, the central charge will change in a specific way. Okay, yeah. Actually, it's quite general. You can do this whenever you have, more or less whenever you have a vector of conformal weight 1. So you start with a Virasoro vector, then it gives you a conformal weight grading, then you take something of grade 1, add a derivative of that on, and then it'll give you a new Virasoro.
I have a quick question.
Yeah.
Do you still, with the new vector B, do you have the T equals the B sub minus 1 as before, or is that no longer the case?
Oh, yeah, I think so. Yeah, that's a good question. I'm pretty sure you do, but I'd have to, yeah.
This shift doesn't affect the constant term, which is where the L minus 1 is. No, the residue, which is where the L minus 1 is. And so it doesn't change that term.
Yeah, okay. Yeah, so.
Thank you.
Yes.
It's a good exercise to check that.
Yeah, yeah. All right, any other questions? Okay, right, so I introduced this new grading, these operators. So I'd better have a good reason for doing that. So I ended the last lecture with Borchard's identity. I want to just quickly rewrite that in terms of this new grading on these operators. Plus, if I remember this.
Your A on the left-hand side, so there's round brackets. I assume you don't want.
Yeah, I'll keep this one with round brackets.
Okay.
Yeah. So let's assume A, B, and C, well, A and B at least, homogeneous with respect to conformal weight. Okay, so we get that. So I commented last time that with this identity, it's natural, or it's easy to write down what a V module should be. So let me say now,
I'm sorry, what does homogeneous conformal weight mean again?
Just that it's an eigenvector. So it's
Oh, I
empty
see.
space.
Got it. Thank you.
Yeah. Yeah, and so and in particular, so this eigenvalue appears here at one place in the identity.
Sure. Thank you.
What should a V module be? It's a I've got an echo here. It's a vector space with, now for each element in the vertex algebra, there should be a field, quantum field acting, which I'll write in this form, AN M. And from the outset, I'll already adopt this new grading, this conformal grading, these A sub n's. There's again a variety of hypotheses you can impose or not. In this case, I'll start from the outset with a grading on the vector space by numbers greater than or equal to some kind of lower bound. And what I want is that this number be basically the conformal weight in the module. So I'm going to impose such that, well, the identity, the vacuum should go to the identity. Borcherd's identity should hold for A, B, and V, and C and M. And finally, that if I consider the field associated to the Virasoro vector, -2, then this alpha should be the L0 eigenvalue, right? So L0 and M alpha should be alpha. Okay, so I hope that seems relatively natural given the structures that described so far. And the question is, like, what can you say about the modules for a given vertex algebra? Okay, so one very important technique that appears in this theory is the Joux-algebra. So let me try to motivate this. So the V module. So it has this kind of top piece of conformal weight alpha 0, right? And then it goes down in steps from there. All right. So let's think about the action of the vertex algebra just on the top piece, perhaps. Maybe things will simplify a bit. Let me do the following thing. Right. So, and I apply, let's see, AM, where M is greater than 0. That's going to annihilate this vector, right? Because this lemma also applies in the module because we just deduced it from Borcherd's identity. All right. So in this identity, if I take M equal to 1, for example, then I get a bunch of terms like A1, and then when J increases, A2, 3, 4, so on, all of these terms are going to annihilate my vector. So this term would vanish. But here I have to take M equals 1.
Just a second, Jethro. Sorry,
yeah.
Your conventions for Z plus, is that non-negative integers?
Includes 0.
Integers? It includes 0. Okay.
Yeah. Okay. So I'll take M equals 1 to annihilate this term. Now, if I took K equal to 1, then this term would vanish as well. I don't want to completely kill everything. So maybe I'll take K equal to 0. Why would that be good? Because then the only term that will appear here is A, something, and B0, right? B0 term here. Actually, so if I've got B0, then maybe I'd want the other term to be just A0 acting, right? So I have two terms composed that both preserve this top piece. So for that, well, M is already 1. So I've got 1, so N equaled -1, right? And then this will be A0. Hand side, I'll just have A0, B0. Following thing happens. So we get delta A. M was 1, J greater than or equal to 0. J minus 1B. And this here was N plus M plus K, which is 0. And it's equal to A0, B0. Okay. So you think of, this is quite nice, right? Take any element in the vertex algebra, it's A0 acts on the top piece, and we have a formula for the composition. Actually, if I did take K equal to 1 in that identity, so that the right-hand side vanishes, then I'd also get something non-trivial on the left-hand side. So let me do that now. Well, let's see, now N should be -2 to have everything be degree preserving. So minus 2, we get delta of aj minus 2 b. Okay, so we've got some subspace of V, right? Well,
I feel like maybe I'm missing something. So is the A subscript on the first term on the right hand side is m plus n minus j, is that correct?
Yeah.
So if you have m equals, say you have m equals 1 and n equals minus 1, then it seems like the j, the 0 terms is, but it seems like none of the j terms would, because
it's true, those operators are non-zero, but they come multiplied by b going up. So the b term kills the vector already. And then you have something which in principle is non-trivial, but it's being.
I see that. I see, thank you.
Yeah. Okay, so let's define I'll do a little circle B. So there are infinitely many products in the vertex algebra. I'm going to introduce yet another one. But it's just some random linear combination of the other products. A j minus 2b, all right? And A with a star, let's say j minus 1b. And let me consider the linear span of all of these circle products. There's a nice thing about J is that J0 on M top is 0. So what we kind of hope to happen is you have a vertex algebra and you have some ideal, something that's hopefully an ideal, you can quotient, and then you have some smaller algebra that acts on the top piece. In fact, this is exactly what happens. So there's actually a whole series of miracles occur now. Fact is that J is a two-sided ideal of this non-associative algebra. And when you divide by this ideal and equip it with this product, it becomes associative. And the vacuum vector, the class of the vacuum vector becomes the identity in this associative algebra with unit class of the vacuum vector. By construction, the top piece of any V module is a module for this associative algebra. So let me give the name for this. So this is called the Joux algebra. By construction, by letting the class of A act by A0, we get a module. The really miraculous part is that this association establishes a bijection on the level of irreducible modules.
And there is no hypothesis of dimension for this theorem. It's any, even if it is infinite dimensional.
Maybe we want countable dimensional.
Okay.
But it's under pretty weak hypotheses. Yeah, it's a pretty general result. If you try to say anything beyond irreducible modules, things become much more complicated. So the Joux algebra apparently sees rather a lot about the representation theory in that it classifies the irreducible modules. But when you look at extensions between modules for the vertex algebra, a lot of this is not seen by the Joux algebra. But this itself holds under pretty general hypotheses. So natural question is, what is the Joux algebra for, say, for the affine vertex algebra? Okay, so it turns out the Joux algebra of VKG recovers very familiar associative algebra, U of G. And this doesn't depend on the level, or rather, yeah, it's always the same algebra. How to see this? So let's just take the vectors corresponding to these generating fields, right? There's this copy of G sitting inside VKG. Then if I take A, circle some arbitrary vector, if you just look at the formula, you'll see that this is A minus 1 V plus A minus 2 V, okay? So in the quotient, whenever you see a vector, so V has a basis A1 minus N1 minus 1, A2 minus N2 minus 1, right? N J equal to 0, PBW basis. Doesn't even matter that it's a basis, it's spanned by such vectors. Whenever you see, if you saw a -2 here, then using this relation, this is set to 0, you could replace it by -1. Right? And similarly, J contains vectors like this. You can show this. So you can, recursively turn any index into a -1. Then you could use the commutation relations to commute it over to this side and then take the next guy. So you can everything, so mod J, V kind of goes to A1 - 1, A2. And then this vector, you identify it with the corresponding product in U of G. Okay, and you need to do a bit more work to show that this is an isomorphism. But at least this kind of makes it believable, I hope. And as an exercise, the identification. So I did this pretty sloppily, but what actually happens is you reverse the order of the terms. Anyway, so if we believe that theorem, which we do, we have a class of VKG modules. Just start with any module for G, and then there's a way of kind of inducing to get a module for the vertex algebra.
Can I ask, for the critical level is different though?
Sorry?
For the algebra is the same also for the critical level, but then the representation theory.
That's an excellent question. So this way of approaching the Jou algebra doesn't really work the critical level because, well,
I think probably not even the definition of a module, because the theorem works for positive energy and you can't really do that without the Virasoro.
Yeah, you can. So I can make two comments about this. So you can do something a little bit weaker than a Virasoro vector. You can you can introduce the positive half of the Virasoro algebra in a way that also works at the critical level. And so I guess that's enough for the Jou algebra. I have to think. Sorry?
You still have a grade.
Yeah. Yeah, I think you have enough of the conformal structure left for it to work exactly the same. The other comment I can make, there is a way to formulate the construction of the Jou algebra in a way that doesn't make any reference to the conformal structure at all. And then you could maintain that definition. But then, I mean, that's something you could do, but since this theorem completely refers to conformal structure, maybe the algebra exists, but you don't know anything about it, or you don't know that it has this property. But yeah, I think even though you don't have a Virasoro vector, you do have kind of a quasi-conformal structure, and I think it's enough. Yeah.
You just multiply the Virasoro vector by K plus your constant and stuff, and that's still grades.
Yeah. I'm sorry?
Just replace the time by
Yeah. Sorry. Yeah, I don't want to say too much about this. So there's a way to more or less explicitly construct this V module starting from the G module. But it involves, you kind of invent a Lie algebra by taking all of these guys A sub n for all A and V and all n integers, and take some sort of universal enveloping algebra. Well, you can put a Lie algebra structure on this, take a universal enveloping algebra. You have to complete so that you can impose Borchard's identity, which involves infinite sums, so on and so forth. And then you can do a kind of induction functor from Jou of V to V of M. Okay. What I want to say now is if you work at an irrational level, this is more or less all you can say, or that's kind of the end of the story. Because this universal affine vertex algebra is simple already. But if you work at special levels, then non-trivial ideals can appear inside this vertex algebra. So let's in fact define LKG to be BKG divided by NK, where NK is the maximal proper. What does an ideal mean? I haven't defined an ideal in a vertex algebra. You can kind of imagine what it might mean. In this case, ideals in the affine vertex algebra are the same thing as G hat submodules. So it's pretty familiar. So there's a maximal proper such thing. We'll divide by that and call the result LKG. So the nice thing about, one of the many nice things about the Joule algebra construction.
It's 10 o'clock. So you, oh, wait, are we going to I've got the time wrong, sorry.
Okay, yeah. But I am disastrously behind schedule.
Not that bad.
Sorry, by ideal here you mean graded ideal in this context?
Yeah.
Okay.
If you don't mind my asking, since we have so many products going around, what product are we using to define this for the ideal?
All of them.
Okay.
Yeah.
Thank you.
Yeah, you'd say, let's say that.
You want it to be two-sided or just one-sided?
Yeah, I mean, that's a good point. It turns out they're the same. So, or rather, there's a kind of skew symmetry identity in the vertex algebra, which is I haven't stated it, but it can be deduced from the other axioms. That basically lets you write anything of the form A and B in terms of B KAs. So any such term is expressed as some kind of combination here. Well, and also this is why I'd like to include T as well.
Sure, thank you.
Yeah, so if you so it's like commutative algebras for this reason, that there's no distinction between left and right ideals. Yeah, but it's from what I've said so far, it's completely unclear that would be the case, but it is. Okay, so the Joule algebra of the quotient is the quotient of the Joule algebra by the two-sided ideal generated by N. Okay. I'm sorry?
It's a two-sided ideal.
Sure. Yeah, generated by the image of the vector subspace. So for example, L1 of SL2. Yeah, it's a bit of a long story. Like you want to think of AN, where A and V and N and Z as a Lie algebra. You can define, so there's this thing Lie V, right? Where you take symbols like this, and you obviously has a construction. So you take this and then divide by T plus dt. Is a Lie algebra. So then you take U of Lie V. So this is a Z-graded associative algebra. And then you have to do some kind of completion because you'd like to, this is kind of too big. You'd like to impose Borcherd's identity. The problem with Borcherd's identity is it involves infinite sums. So you take some sort of completion, and then you quotient by Borcherd's, and we'll call this like U of V. So it's some huge topological associative Z-graded algebra. And the Joule algebra appears, so it has so U of V0 maps to the Joule algebra. And in fact, you can prove something like U over actually is the Joux algebra. Yeah, and then then really it's induction in this sense. Yeah. Yeah. Actually, what I've just described, so that would be, I guess,
Maybe M.
like that.
Yeah, we need to see.
Yeah, and then something you could do is then quotient by the maximal submodule that doesn't meet the bottom part. Yeah, and that gives the bijection. So this guy is V1 SL2 over N, where N, it turns out, is generated as a G hat module, let's say, by E minus 1 squared. Okay, so it's kind of fact from the algebras. Minus 1, H minus 1, E minus 1, E minus 1 squared. Yeah, so this guy is then, generating some submodule. So it turns out that the Joux algebras, this associated U of SL2 modulo the two-sided ideal generated by E squared. So you can compute it pretty explicitly. So now this diagram I'm drawing U of G. So like F H E squared. So if this two-sided ideal contains E squared, then it contains, for example, the commutator of F with E squared, which is something like EH plus HE. Okay, so the two-sided ideal contains this element as well, which lives here. And then you could take commutator again, get a vector here and here. And with a bit of work, you can prove that in lower degrees or higher degrees, whatever, everything goes into the ideal. So the Joux algebra is actually 5-dimensional. In fact, up to isomorphism. So if you play around with idempotence and all this usual associative algebra stuff, you find that this is isomorphic to 1-dimensional associative algebra, direct or products, matrices 2 by 2. So that's where the 5 comes from. Which has 2 irreducible modules, trivial module and a 2-dimensional module. So the Vertex algebra has 2 irreducible positive energy modules, whose lowest pieces are dimension 1 and 2. So one of them is the Vertex algebra itself, and the other, it's not really visible. The other has this top piece, this little 2-dimensional representation, and then induce like that. All right, 20 minutes. Any questions? Okay, so you can proceed in this way, but the computations get pretty onerous. So let me start introducing a bit more theory. So affine Lie algebras. Admissible weights. What are admissible weights? So there's this sort of usual thing in theory of affine Lie algebras where in order to have a good highest weight theory, we extend the Cartan subalgebra a little bit. So Cartan H is going to be, so you take the dual of the finite, the Cartan of the finite Lie algebra, and then you're supposed to add in 2 extra guys, delta and call it lambda 0. Okay, so kind of conventional. These are supposed to satisfy lambda 0, delta. These things are all orthogonal, except that delta, lambda 0, their pairing is 1. Okay, so I'll draw a picture now. So if we think of SL2 hat, so SL2 itself, E, H, F, and then we kind of want to organize all the other elements by going into the second dimension. So here's HT, FT minus 1, for example. And this is compatible with the grading in V that I described, which is a G hat module, right? So each of these points we also think of as a weight. This weight here is alpha 1, let's say. So a simple root of the finite guy. And then delta, you should think of as sitting up here. This is delta, okay? And then lambda, if you like, maybe sort of comes out of the page. Okay. So the simple roots of this, so you can, famously, affine Lie algebras are examples of Kac-Moody Lie algebras. So they have Cartan matrix and all the usual theory simple roots. So what are the simple roots? Simple roots in this case are this simple root of the finite guy, and this one alpha 0, which is, well, is a delta. In this case, it's minus alpha 1, and in general, it's minus the highest root of the finite root system. This is a very familiar notion of dominant integral weight lambda. If when you take your weight lambda and you add to it the Weil vector, which remember is the sum of the fundamental weights, pair it with any positive weight, then you get a positive integer. So the point is integral and positive. And here delta plus, also neglected to mention in this case here, delta plus is everything up from that diagonal line, right? So more generally, and what is rho? Rho, the Weil vector, the only important thing about it in this case is that it's the Joule-Coxeter number times lambda 0, the finite Weil vector. Okay, so this dominant integral, more generally, weight might not necessarily be integral, but we define the subset of roots such that lambda plus rho alpha is integral, right? So call that the integral root system of lambda. Okay, so this is a pretty natural generalization of dominant integral. It's saying that for any given weight, we look at those roots that pair integrally with it, okay? Now, I mean, if lambda is really crazy, then that could be nothing, so that's not very interesting. So we demand that that root subsystem is pretty big. In other words, has the same rank as delta, but in general, it's going to be some non-trivial subset. And then we want to impose the dominant part, which is saying that, well, if you take those roots in there that are positive and you pair lambda plus rho against them, then again, you get a positive integer. Okay. So perhaps visually, it's a little bit hard to wrap your head around at a first pass. But really one of the exercises is to work it out. First thing, for example, when is k lambda naught admissible? So k lambda naught against the finite roots gives 0. So all of these finite roots are in this delta lambda. On the other hand, right, so we've got this guy, delta lambda. Now, if alpha 0 were in here, well, then it would just be dominant integral, right? So if not, then maybe 2 times delta minus the, well, the question I'm asking is, if the rank is going to be the same, then there has to be some first level above the floor where you find another root in this integral root system, right? So I'll call that number q. So let's say q delta plus some finite root is going to be the next guy in this integral root system. But since all of the finite roots are already in the root system, so you can just subtract and subtract, and the lowest one of these would be minus theta plus q delta. So this set, I'll call it pi q. This is going to be the set of simple roots for the positive root system of lambda. Well, okay, so we're finding that this weight paired against q delta is giving an integer. So that means that the denominator of k is q. So k, in fact, so there's a correction that appears because we're adding and subtracting this Weil vector at every point. And the Weil vector involves h check times lambda 0. So in fact, k has to be of this form. And then dominancy implies that p has to be at least h check. So I know I'm going through this very quickly, but this is what ends up happening, okay? So these levels are called admissible levels. And then LKG, which as a G hat module is L of k lambda 0. called admissible vertex algebras. So theorem of Arakawa, which I've kind of butchered because I've not exactly true as stated, but it's morally true. I'm omitting some cases. Is that so you want to know, so you have the Joux algebra of the universal enveloping algebra, right, is U of G. Since we're at some special level K, an admissible level, there is some non-trivial ideal. So the Joux algebra is some non-trivial quotient of U of G. So then you can ask, which irreducible highest weight modules for U of G descend to modules for the Joux algebra and therefore can be induced to get modules for the vertex algebra? And the answer is they're precisely all the other admissible weights of the same level K. So we've got one of them, K times lambda 0, where K has to be one of these special levels. V itself is the induced module corresponding to that weight. And then you have this finite collection of other weights, admissible weights of the same level, and those give the other modules. So what I had wanted to do in this lecture is explain the theory of Kazhdan-Lustig tensor product and how you prove this theorem using that, but out of time. So until
Well, thank you, Jethro, for being so pedagogical and not racing through the tensor products. Are there any questions?
It's a bit a stupid question, but I don't understand the last statement. So
it's because the grammar is not right.
So L lambda is a Verma module.
Sorry?
What is L lambda?
Lambda. So let's see, the irreducible positive energy modules induced from the.
Right. L lambda is a module for the finite Lie algebra.
Okay, so lambda is in H star and not H at star.
You have to project onto the finite Cartan, right?
Oh yeah, that is a yeah, I guess.
So it's irreducible module associated to this weight.
Associated to?
L lambda is the irreducible module associated to lambda, the quotient of the Verma module by maximal L.
Yeah, is irreducible?
I just don't remember what is L lambda.
Yeah, what should I say?
Okay.
Positive energy. Yeah, that's what I would say.
And so it's induced in the sense of before from the module.
Yeah. Or I guess what I also could say is that those, you have some, I mean, in principle, and indeed this happens, so you have some V module whose top piece is some very large, possibly infinite in both directions, G module, right? So I'm saying this theorem is not making an assertion about those modules. It's saying if the top piece is a highest weight module for G, then the module that you're restricting is one of these admissible irreducible modules. Of little k. Yeah. Also, the statement's not quite correct in the sense that there should be those admissible weights whose integral root system is conjugate by an element of the affine Weil group to pi q. And also, these so-called admissible levels are slightly different if the finite Lie algebra is non-simply laced. There's a complicated interaction between what happens when the denominator is not co-prime to the lacing number of the Lie algebra. So there's a distinction between what are called principal and co-principal admissible levels. But I've tried to make everything as simple as possible.
Are there any other questions? If not, then since there's already been quite a lot of questions, I think we can call it out. So let's thank you.